Hello everyone, and welcome to another GIS lecture video. And in this lecture video, I want to redo our discussion on this idea of using a standard grid to generate some measure of a feature pattern. So we're going to do the equal area grid. And I feel like our previous attempt to explain this wasn't very clear, so I want to go through a more concrete, defined worked example. And so we're going to go through the same concepts, just with a better example. So in order to have an equal area grid approach, what we're going to do is we're going to first create a fishnet of equal size grids. Right, and we did that here. So this is our example. There's 150 points. So using our notation from before, right, n in this case is going to be 150. And then we've seen that notation m used to denote the number of quadrants in the data set. You also will sometimes see this referred to as k. I prefer to use k, so we're going to use k. So in this case, k is the number of quadrants. We have 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So we have 25 quadrants. So 150 points, 25 quadrants. So this is points. And this is quadrants. Okay, right? So we've created a fishnet of equally sized grids. Check. Each one of these grids is 5 by 5. Next, we need to count the points in each grid. Right. So we're literally going to count them. 1, 2, 3, 4, 5, 6, 7. So this would have 7. Generally speaking, I'm going to do things that are on the top line down. If they're in between, they're going to go up. If they're on the side, they're going to go right. So if there's any confusion in how I'm counting them, this would go here, this would go here, this one will actually go there. Just in terms of counting. So this grid cell is going to have 7. So what we're going to do is we're actually going to repeat the process for all of these grid cells. Okay, so I've just quickly finished counting the number of points in each grid cell, and then this number here just represents the number. Okay, so once we've counted each point in the grid, we convert this to a frequency table. And what that frequency table is going to look like is it's going to look like this. So we're going to kind of flip this idea. So we're going to go from the number of points in each quadrat to the number of quadrats with a given number of points. All right, so this is going to be number of points. And so we have some with 3, some with 4, some with 5, some with 6, some with 7, some with 8, some with 9, and some with 10. Now we don't really have 8, but because it's in the sequence, we're going to include it here. And what we're going to do is we're going to count up the number of quadrats. Right, the number of quadrats. So this is the number of points. This is the number of quadrats containing those points. Right. So we're just going to say, okay, well, how many quadrats have 3? Well, we have 1, 2, 3 with 3. How many quadrats have 4? 1, 2, 3, 4, 5, 6, 7. Right, and then we're going to continue this process of just looking at the number of points and then counting the number of quadrats that have the number of points. Okay. And so you see that I've just finished doing the counts. So again, just to reiterate, for example, this line right here is saying that there are 2 quadrats that contain 9 points. Okay, that's all this is doing. And just to remind ourselves, if we add up the number here, we should get 25. Okay. So then what we want to do is we want to convert this table here to what is called a proportion or a probability table. So we can convert the frequencies to proportions. And all we do to do that is simply divide each row, each row by the total, right? So this, we're going to call this P of n. So this is the probability or the proportion of quadrats under this specific observed data set that have this number of points in them. So this right here, just to sort of show you how this would work, right? This one right here, this is going to be 3 over 25, right? This is the probability or the proportion of quadrats that have 3 in them. And so if we do that math, what we get is we get approximately 0.12. Okay, right, so we get a 0.12 for this. We would then do the exact same thing here. So this would be 7 over 25, which is going to give us 0.28. 6 over 25, which is going to give us 0.24, and so on. Okay, so you can see here that I've just finished doing the math. So all of these now have a associated probability or a proportion. And you can see here that if you do the math on this, all of these should sum up to 1, right? That's just how we've sort of defined this division here, right? Each of these is a proportion of 25, so the total number is 25, so the total proportion should be 1. Okay, so this number here, then what we need to do is we need to convert this to the cumulative probability, right? Which I'm going to call C of P. This is just the cumulative probability. Right, cumulative probability or cumulative proportion. And literally all we're going to do to get this cumulative probability is we're going to add this column. So we're going to take one row and we're going to add it to all of the rows before it. Right, so this row is 12, there's no rows in front, so this is going to be 0.12, right? This row is going to be 0.28 plus 0.12, which is going to be 0.40, right? This is going to be 0.24 plus all of the rows before it, so that's going to be 0.64, right? 0.12 plus all of the rows before it, or 0.76. Right, 0.88. This one doesn't have anything added, so it is also 0.88. 0.08 plus 0.88 is 0.96. And then finally, we add that 0.04 to get ourselves back to 1.0. Right, so again, cumulative probability, we're just taking whatever this row is and adding it with everything above it. Okay, that's all we did there. So now we're ready to move away from this measured data into talking about what we would get if we expected random. So let's go ahead and give ourselves just a little bit of space here because we don't need to worry so much about the visual anymore. Now we're going to start focusing in on this proportion table. So now what we need to do is we need to figure out what the expected random distribution would be. Right, so now you need to figure out the random distribution. Well, to do the random distribution, under this case, what we're assuming here is that the random distribution would end up, on average, with the same number of points in each grid cell. All right, so random in this case just means equal numbers in all grid cells. Right, and so to figure out what that looks like in terms of what an equal number of grid cells would be, all we have to do is take the total number of points that we have and divide it by the total number of grids that we have, right? Because this equation right here, taking the total number of points divided by the total number of grids, would give us an average number or an equal number of points in all cells. And the equation has a special symbol, lambda. Right, so this is lambda. This we already know is the number of points. And this k here, this is the k from here, so this is the number of quadrats. Okay. So we can quickly do the math for our own new data set here. And what that's going to look like is our lambda is going to be equal to the number of points we said was 150. Our k here we said was 25. So 150 divided by 25 should give us 6. Right? 150 divided by 25 should be 6. So our lambda in this case, the average number of points per quadrat, or put another way, making sure that every grid cell has an equal number, well, that number would be 6. Okay? So that helps us, but now we need to figure out, okay, given the same distribution of points, right? 3 points through 10 points, and this expected average, what would we get in terms of a probability of having that number of points in one or more of the grid cells? And so what we do to figure that out, let's actually formalize this, right? So we figured out the random distribution. Now we need to calculate the probability of a given number of points in a grid cell under this random distribution. Right, okay. So what is that going to look like? Well, we have our lambda here. Let's give ourselves just a little bit more space. I'm actually going to take this table with us so that we can work on this table. Let's go ahead and give ourselves a little bit of space here. Copy the table down over here. All right, so if we want to calculate the probability under this new random distribution, which we said has an average grid cell count of 6 points, how do we figure out what the probability is of a grid cell under that distribution having 3 points in it? Well, there's an equation that we can use that looks something like this. The probability of having X number of points is going to be equal to e to the negative lambda times lambda to the x over x factorial. Okay? So what this equation is saying is this is the probability of a quadrat containing x points, right? This x here, this is the number of points. Lambda, we already know what lambda is. This e here, this is a mathematical constant. 2.7183. Okay. Right, so what we're saying is we have this constant and we're taking into account the number of points we want, as well as this average that we calculated for a random distribution. We can plug these in for a given number of points to get the probability of a quadrat containing exactly that number of points. So let's go ahead and do that example for 3. All right, so the probability of a grid cell containing 3 points exactly is going to be equal to 2.7183 to the negative 6 in our case, times 6 to the 3 divided by 3 factorial. Right, so all I've done here is I've replaced x with 3 because we're worried about 3 points, and then I've replaced everything with the numbers that we've already calculated. So if you do the math on that, what you get is a probability of approximately 0.0892, right? And so what we've just calculated, if we want to add a column to our table here, right, is this probability of n, and I'm going to put a sub r here to indicate that we're talking about the random distribution. So what we've calculated here is the probability under this random distribution of getting 3 points, right? So this would go here, 0.0892, right? So again, what we calculated was just the probability of under this assumption of a random distribution of getting a quadrat with 3 points. So what I want to do now is I actually want to switch over to an Excel sheet because this is getting a little bit messy, and that way we can see things a little more clearly. Okay, so this Excel sheet has the exact same information that we just talked about. I've made one small change. I've actually added the values 0, 1, and 2, even though we didn't have quadrants for them, as well as extending from 11 to 16. And the reason I did that is because our random distribution is not necessarily going to adhere to the strict subset of numbers that we found in the observed data, right? You can see that there's a non-zero probability of having quadrats with nothing in them, and there is a non-zero probability of having quadrats with 15 in them. And since the point of this is to end up with a cumulative sum, we want to make sure that everything sums to 100. Now, in reality, for the analysis that we're going to do next, the 11 through 16 aren't actually important because we only go up to 10 in the quadrants, but the ones beforehand are definitely important because there are non-zero probabilities of having fewer numbers of points than the smallest that we observed. So hopefully that makes sense. Again, all I did is we had our first number of observations was 3, but because we're dealing with a random distribution, there is a non-zero probability that we could get less than what we observed, and so we have to include those, right? So I included 0, 1, and 2 because for the random distribution, that matters a lot. And you can see that I've done the exact same thing as I did with the previous example. So this 0.089 is still the probability of 3. And what I've done is I've included this column over here that is the cumulative probability. So it's the exact same thing we did for the observed data, where we just add the probability of one number to the probability of all of the previous numbers, right? And so it's this column right here. It's just that cumulative probability. Okay. So in order to determine whether or not our observed patterns are statistically significant, what we do now is we take the difference in cumulative probability between the observed and the random. So put another way, it is this number minus this number. Ooh. Yes, accept the change. All right. It is equal to this number minus this number, right? It is the absolute value of this number of the difference between what we would get for cumulative probability under random minus the absolute value of what we get for cumulative probability under the observed, right? And so we're just going to drag this down here. Okay. And so now what we've done is we've just taken the difference for every number of points, the difference in the cumulative probability of that occurring. And then what we do is we highlight the most extreme difference, right? So we basically look through this list of differences and we find the highest value. So in this case, it's this value right here. So I'm going to pull this out. So this is our most extreme difference. Okay. Actually, let's actually move that some over here so we can do that. All right, that's our most extreme difference. Okay. So we now have our most extreme difference. And what we're going to do is we're actually going to compare this most extreme difference to what's called a critical value or a critical threshold. Okay. This critical value is going to be calculated based on two things. And I'm actually going to pop back over to our paint here and talk about this equation. So what we've done up to this point is we've calculated our cumulative probability for the random distribution. To add, just to kind of keep our list going here, I'm going to give ourselves a little bit more space. So the next thing that we did was we took the difference in cumulative probability. Right, that was the thing that we just did in Excel where we took the difference between the cumulative probability of what was expected and the cumulative probability of what was observed. Then we found the highest difference. Sorry, I'm mixing my tenses here. We took the cumulative probability, we want to find the highest difference, or the largest difference, I should say. Right, find the largest difference. Right, and that's what we've done so far. Then the last thing that we want to do is we want to compare that difference to a critical value. So what is that critical value? Well, that critical value is going to be based on two things. So we have our critical value, which I'm going to call CV. This critical value is going to be equal to K over the square root of M. And I really wish that it wasn't set up this way because we're mixing variables here. But note that in the case of critical value calculation, this K is a constant. And this M is representing the number of quadrants. Okay, and so there's a lookup table that we would use to figure out what K we want, but basically it's going to be a constant that's going to change based on the level of confidence. Right, so let's say that we wanted to be confident at 80%. Right, so for 80% confidence, right, we would want to calculate our constant to have a value of 1.07. Right, so this 1.07 is the value for this constant at 80% confidence. What we do is then we just divide by the square root of our number of quadrants. So for our specific example, our CV is going to be equal to our K of 1.07 divided by the square root of our quadrants, which is 25, which is 1.07 divided by 5, which if we do the math on that, we get a value of 0.214. So this is our critical value. Just to really quickly grab our value from our actual value. So this was, we calculated it as 0.214. Right, so we have our most extreme difference and we have our critical value. So there are two scenarios. The first scenario is that the extreme difference is larger than the critical value. That means that your result is statistically significant. If your extreme value is less than the critical value, that means that your result is not significant. Okay? So in this case, right, our extreme value is less than our critical value, which means that the results of this analysis are that the distribution is not statistically significantly different from random. So let's go ahead and wrap this up by finalizing what we've done here. So our actual max difference, just to be clear here, was 0.194. And we have two choices. If max difference is larger than CV, the result is significant. Right? If the max difference is less than CV, the result is not. Okay? So again, in this particular case, we went with 2.14 was our calculated 80% confidence. Our maximum difference was 0.194. So because this value was less than this value, right, the max difference was less than the critical value, we would say that this result is not significant at the 80% confidence level. And in case this isn't clear, right, increasing this confidence level to 95 would only make this situation more extreme, right? We're not going to be insignificant at 80 and then magically become significant at 95, right? It just doesn't work that way. The more confident we are, the less likely we are to get the result. So hopefully this all makes sense. And as always, if you have any questions, please reach out. Thank you.